Okay, let's continue with our discussion on transition metal complexes. Now that we know how to name them, let's talk a little bit about their structure. And the main thing we want to focus on is isomers. So isomers, they have the same molecular formula, but they have different arrangement of atoms. Could be through bonding, or it could be through just through space orientation. So the first one, through the bonding, they're called structural isomers. Okay, so this is different bonds. Okay, and the first one are linkage isomers. Okay, so we'll talk about what they are. Basically, we're going to focus on the nitro group. So from nitrite ion as my ligand. Okay, and then the other part, they're called coordination sphere isomers. And just so you're aware, when we talk about coordination sphere isomers, typically we're going to be looking at the solids here. Okay, so basically, what do they look like? When we talk about stereoisomers, we have mentioned before the geometric isomers in the context of, we saw the cis and the trans. We were talking about the intro to Werner's theory. And what we'll do is we'll go into more detail on that. There's another one, and it's FAC and MER for meridian, so on the face, facile and meridian, and then optical isomers. And these, they're also known as enantiomers. So we'll spend some time with enantiomers. Okay, so let's go through and we'll talk about the different types of isomers and what they are, and give you examples. At the very end, we're going to go and put together the flow chart so you say, okay, what kind of isomers do I have? All right, so let's take a look at structural isomers. The linkage isomers, they're rare, but they're quite interesting. Okay, and what it is when we look at linkage isomers. Okay, so let me give you, let's do this. Let me give you okay. Compared to, so this is what, a penta-aqua nitro. Let's talk about the names. Okay, cobalt 3. All right, so let's compare these two linkage isomers. Okay. In the center, I have my cobalt. Since it's cobalt 3, we know it's going to be octahedral. I had 5 waters. And the difference was here. The first one was bound to my nitrogen. Okay, so what we do is we call this a nitro isomer. So if you just say, oh, this is nitrate, it's a negative ion, so we end in O. This tells me it's bound to the nitrogen. But as you know, we had two possible donor atoms, either the nitrogen or the oxygen. So if we bind it to the oxygen, okay, so here I'm going to bind it to my oxygen. Let me just, okay, because it's bound to the oxygen instead of nitro, we say nitrito. So we change the ending to indicate it's bound to the oxygen versus bound to the nitrogen. Okay, so this is a linkage isomer. Same type of bonding except for this very last one. This one is a monodentate, but since I have two possible donor atoms, the linkage isomer is just binding to the different donor atoms. Nitro, nitrito. The only other one that we showed you was going to be the thiocyanate. Okay, so like I say, it's interesting that we do this. This is probably the more common bonding situation through the nitrogen, but it's possible to get it through the oxygen. Okay, so that's your linkage isomer. Let's talk about your structural. These are both structural. Let's talk about your coordination complex. Okay, so when we talk about our coordination complex, then it's going to be here. Let me just show you. So remember our coordination sphere. Okay, remember in the very beginning when we talked about Werner theory, we talked about my cobalt-3 chloride that's bound to different, well in that case it was different ammonias versus okay, so when we say it's the same formula, we're really looking at that part, okay? Or I can give you a different one, okay? Let's see. And let me just go ahead and leave it this way, all right? So when you look at this, remember we had my cobalt, this first one, had a different coordination sphere. Okay, so this had a different coordination sphere than this one. Okay, one moment. Okay, so the second one has a different coordination sphere. Okay, so the bottom line with this one is I have a different number of ammonias bonding to the cobalt and the chlorine. And you say, oh, well, wait a second, how do I know this? It's only when you start crystallizing out, you start seeing the different colors. Because if we take a look at something instead of ammonia, like when we take a look at something with water, okay, then you can still have the same thing. You can have 6 waters complex with a cobalt, okay. You can have 5 waters complex with your cobalt, okay, or even 4. But the bottom line is this: when you look at your coordination sphere, that's when you can really tell. Because in all these cases, they just look like hydrates, okay. So if you look at your hydrate, if we wrote CCl3, 6, you would say, okay, it's just in my crystal structure, and you wouldn't be able to really distinguish between them. So it's by knowing that you have a different coordination complex. So these are coordination sphere isomers. Okay, right there. Because this is just basically having solvent crystallized with it, you would think. But when you see the coordination sphere, then you can detect the difference. Okay? What's more interesting, and you'll see more commonly, would be stereoisomers. Okay? So with stereoisomers, okay, you're going to have the same bonding. Okay? The previous 2 that we looked at, we had different bondings. The linkage bonded to a different donor atom. The coordination sphere, you had different ligands. The total molecular formula was the same, but you're going to have different ligands actually bonding to your metal ion. So let's start talking about stereoisomers. Okay, let's talk about some stereoisomers. So stereoisomers, unlike your structural isomers, stereoisomers have the same bonding. Their only difference is orientation in space. And the reason that the orientation in space is important is because you can't change it. When you're around a single bond, you can rotate. Molecules are always in motion, but there are certain types of bonding situations where you can't change their orientation. And so therefore we get stereoisomers. So the first set of isomers we're going to talk about, actually, they're called geometric isomers. Okay? And we talk about this, and there are 2 examples. Now let me give you the examples with the organic compound first. And why is that? Because we already talked about hybridization, sigma bonds, and pi bonds. And we were talking about how pi bonds, you have a difference. You can't just freely rotate around it. And so the orientation in space here, when my 2 groups are on the same side, this is a cis isomer. But when they're on opposite sides, this is a trans isomer. So we have that same situation, actually, when we look at our transition metal complexes. So if you recall, when we were looking at a cobalt compound, it was cobalt, it was NH3, so the tetraamine, okay, chloro cobalt 3 chloride. Okay. So let's take a look at this. And we had 2 different compounds. We had one missing a, oops, sorry. I'm missing my 2 here. Tetraamine dichloro, cobalt 3 chloride. I'm sorry. That was an error there. So, tetraamine dichloro, cobalt 3 chloride. And we had 2 different coordination spheres. Okay, we had this one and we had this one. They both have the same molecular formula. They both have the same bondings. This cobalt is bonded to the nitrogens of 4 ammonia molecules and to 2 chloride ions. And that's the same for both cases. The difference is this. These 2 chlorides are on the same side of my cobalt. So this is a cis isomer. This one on opposite sides of the cobalt. This is a trans isomer. They have different physical properties, different colors. These are geometric isomers of each other. Okay. There's one other. If you look at a situation like this, suppose we took something like, let's just give you, okay, so let's take a look at this type of iron complex. I should find one. Okay. This complex, this coordination sphere, is going to be different than this coordination sphere. Let me just draw it out for you. Okay. So how are they different? Again, these 2 are geometric isomers. But if you look, if I took a plane right here, these 3 are on the same face of that plane. Okay? And so actually, this is facile, or we abbreviate it face. Okay? So this isomer is different because if you look at your waters, Now, if I look at the waters, the plane they're in, they're on the same plane here. And look at my ammonias. They're on the plane 90 degrees from it. Okay? So, we call this meridian. They're on the same meridian, or mer. Okay? So they're on the same meridian here, here. This one, if you look at dividing, they're on the same side here, the same face, or the same face. So these two are also geometric isomers. Okay? So, these are the types of geometric isomers that we actually encounter when we look at complex ions. What other type of isomers are there? Okay. Let's spend a little time with this. Okay. The other type of isomers that we're talking about, okay, they are called optical isomers. Okay, or the more common term, enantiomers. Okay, what this is they are mirror images of each other. And you need to know that the mirror image is not superimposable. If they're superimposable, then it's not even the same compound. Okay, so let's take a look. Okay, when you have enantiomers, they're mirror images of each other. Mirror image is not superimposable, so we say they are chiral, which means handed. Okay, so if you look at your left hand and your right hand, let's see if we can draw. Okay, so right hand, this is my palm. Okay, so this is my right hand. This is my left hand. And they look like they should be the same hand, but they aren't. Because if I try to get the palms the same way, my fingers won't match. If I put the palms together, my fingers match, but it's outside and outside. That's not superimposable. So the left hand may be the mirror image of the right hand, but it's not superimposable. So your hands are chiral. Okay? So let me just give you, if I look at, let's say, tube socks. Okay? These are what we call achiral. Because basically, you can't tell the left sock from the right hand sock. If you look at driving gloves, well, they're handed. And in fact, if I put my right hand and try to put it in my left glove, it would not fit. Or if it did, it'd be most uncomfortable. Okay? So to determine whether something is an enantiomer with something else, if these two things that you're comparing are optical isomers, okay, you're going to take the mirror image, and then basically you're going to see if you can superimpose it. Okay, so if I have molecules, if they are optical isomers, their physical properties are the same. Okay, so if they're the same, how can we differentiate them? Okay, what they do is they rotate plain polarized light in opposite directions. Okay, so we say they are optically active. Okay, so let me try to draw you an example of a left-handed and a right-handed molecule, or optical isomers. And then we'll talk about what does this mean, okay, and the terms involved with that. So we're going to take cobalt again, okay, and we're going to take cobalt, so it'll be tris, ethylene, diamine, cobalt 3 ion. Okay, so let's take a look. Here's my cobalt. Okay, let me draw the mirror image. Okay, so here's my cobalt. Okay, so far so good. Okay, now this is my mirror plane. Okay, so now let's go ahead and put in my ethylene diamine. So I put in my ethylene diamine. The first one, let's say, goes in this direction. Okay, NH2, and I'm just going to draw a ribbon. So this stands for the CH2, CH2. Then here's one. And then here's one. Okay, now if we try to draw the same thing, the mirror image, I have an NH2 here and an NH2 here, and my ribbon goes here because that's closest to my mirror, so that's going to be close to my mirror. And the way to check it out is just stand in front of a mirror and hold something to it and see. If my pinky's closest to the mirror, then on the other side the pinky's going to be closest to the mirror. So if these two NH2s are close to the mirror, then those two NH2s are close to the mirror. If this top one goes to the dash, then this top one goes to the dash. And then we have the bottom one. Now, if you try to superimpose it, okay, so now if I take this and I try to fit it on here, if I match these two, then these would be in the wrong orientation, okay? If I just try to rotate it this way, right, this would be in the back going down here, not in the front. So if you made just like take some noodles and try to do this, but if you try to make these, you'll find that they are not superimposable. Therefore, they are enantiomers of each other. Okay, so they are not superimposable. If you try, you'll see they are not. They are enantiomers of each other. So let's talk about this rotation of plane polarized light, so you know what I'm referring to and the terms that we talk about when we describe them. And then we'll go ahead and do our flow chart. Okay. So what happens is this. If we have a light source, okay, there. What happens is the light shines through a polarizing filter. Okay, so when I look at my light and it's shining through, my light is in all these different random directions. When it goes through my polarizing filter, all of the ones that don't match my filter get stopped. The only ones that pass through is in the same orientation as my filter. Okay, so this is like if you wear polarizing sunglasses. The glare actually gets reduced because a lot of the light doesn't get allowed to get through. It gets actually blocked from your polarizing filter. Okay, so as it goes through, then it goes through a solution that contains your sample. Okay, when it does that, finally it goes through a detector. Okay, oops, I can't draw a circle here. This is my detector. And here's your eye. And when you look at it, this is 0. Okay, in that plane. But if my sample is optically active, it can rotate light by an angle alpha to the right, or it can rotate light to the left. Okay, so one enantiomer will rotate to the right. The enantiomer to that compound will rotate to the left by an equal amount. If your sample rotates light to the right, you call that dextro, because dextro means right, rotatory. So, right, and it's a rotation. Okay? We often designate the actual angle as positive. Okay? If we rotate light to the left, okay, that is called levo, which means left, rotatory. And you can see us designate, it's got a negative, okay, in parentheses. or you can see it as a italicized D or L. So plus or D means it's dextrorotatory. Minus or an L tells you it's levorotatory. Okay? But in either case, remember, when you have a value for this, it means that your sample is optically active. Alright? Okay, so now, let's take a break and start talking about color, magnetism, and crystal field theory.